Hey everyone, welcome to my talk on operators, EDR sensors, and OODA loops, understanding and exploiting defensive loops to win operations. It's an honor to be able to present this, and I wanted to thank you for taking the time to watch this, and a big thank you to the organizers of ZeefCon for the work that they do behind the scenes. I also started a blog post series on how to evade EDRs, or APPs as some might call them, but I just haven't gotten around to completing it. It's something I'd like to get back to later when I have the time. But if any of you have been following that, then you can consider this talk as another paradigm to think about the same topic without necessarily supplanting the paradigm in that series. I'm also aware that I certainly have gaps in my understanding on this topic, so I welcome any critical questions or comments that come out of this so that my assumptions can be challenged, and I think it's also a great way to learn. Just so I'm not wasting anyone's time, I wanted to say that this talk isn't about some special secret sauce or universal silver bullet that can bypass EDR products. Instead, this talk is about how we make decisions as operators and how we can use that to our advantage when up against Ddr sensors. So on the side you can see the agenda. I'll go over OODA loops for those that aren't familiar with them, as well as my interpretation of how that applies to operators. Then we'll go over how to leverage that same decision-making process we use as operators to understand how EDR sensors work and how to circumvent them. And lastly, I'll sum it up with some takeaways and things that you can consider as you're in the process of evading EDRs. So my name is Jackson, also known on Twitter as Jackson T. A bit about myself. I did my bachelor's degree at the University of Toronto in Canada, which is where I'm from. I majored in public policy, did a double minor in psychology and computer science. My hobbies are in red teaming and vulnerability research, and I used to work for Disney's internal red team, and prior to that I was a consultant at Security Compass, focusing on application security and vulnerability research, which is how I got my start in this field. I bring up the social science background because although I'm definitely not an expert, I like to understand how people think and how they make decisions. Some might recognize the avatar there as the logo for Kumon. It's what they call the thinking face. When I was a red team operator, our operations were very scenario-based, and we had a specific starting point and a specific business goal to reach at the end of the op. One of my favorite parts about each op was this process where, as a team, we reasoned about our current situation, and then we decided what our next course of action should be. And we would do this again and again and again as we inched closer to our goal. What it came down to was this repeatable or looped process, where as operators, we observed the environment we were up against, then we identified our options, we weighed them, and then we selected one that we acted on. Of course, this situational awareness and tactical decision-making isn't really unique to red teaming. It can be applied to many areas of life, and it's one of the focuses of the cognitive sciences, operations research, military psychology, and more. And that's what eventually led me to John Boyd's work on what he called the OODA loop. I'll give you a moment to take a look at this, especially for those of you that aren't already familiar with it. So to give some background here, John Boyd was a fighter pilot and strategist in the US Air Force, and he came up with this OODA loop model while analyzing dogfights. OODA stands for Observe, Orient, Decide, and Act, and this loop provides a structured way of transforming the information we sense and perceive into action. It's a way of showing how we make complex decisions based on limited context and evidence of unfolding situations. To speak a bit about each process, we start with Observe, which is scanning the environment and gathering information from as many sources as possible. Then we have Orient, which is analyzing the information we get, synthesizing it into meaningful knowledge where we can understand what options are available to us and what we can do with them. Then we have Decide, which is considering those options and then selecting a subsequent course of action. And then finally Act, which is carrying out that selected decision. As you're looking at this and are internalizing for those that aren't already familiar with it, it's worth noting that this isn't a single-threaded flow where you just focus on these one at a time in isolation. Instead, these are parallel and interrelated processes that you continuously cycle through. In the next few slides, I'll go over what this loop looks like for operators, at least in the way that I'm interpreting it based on my experience, and then I'll provide an example after that. Before I begin explaining the operator's OODA loop, it's worth saying that number one, this isn't the main part of the talk, and number two, this is most likely stuff that you already do, and there's really nothing particularly new to learn from. So why am I talking about this? Well, the idea is to take a step back and explain our day-to-day work in the context of this model so that when we go over EDR sensors later with the same model, we can see the parallels more clearly. Starting with the observe process, this is where we seek and gather information from our environment, and it gets fed into the Orient process. So from an operator standpoint, I look at this as a combination of what we gather from the target environment and what we gather outside of it. So from the target environment, this can include things like enumerating a target company's subdomains or open shares in its network, and it also includes observing the consequences of our actions, whether what we did brought us closer to our objective or further from it, and whether it raised suspicions from defenders. And self-growth also plays into this, where we're gathering information about the latest TTPs from our Twitter feeds as an example, and just generally speaking, continuously consuming other material that help us learn and grow. Next, we have the Orient process, which is where we analyze and synthesize our observations and then produce options as a result. You can call them solutions or paths. I use them somewhat interchangeably in this context, but this is basically where we ask ourselves, what does this information mean to us, and what can we do about it? And I think this is why tools like Bloodhound, Auspex, Grouper, etc., they provide a lot of value because they're good at automating some of the observe and orient parts for us. For example, with AD, the Sharphound collector serves as an active observer to gather information about the environment, and when the results of that get fed into Bloodhound, we can get a sense of what options or attack paths are available to us to reach a certain resource. When I look at the paths available to us from an evade EDR or EPP standpoint, there are these four categories of options that come to mind. The first one is avoidance, where you just avoid directly operating on systems that have the products installed. Companies often have saturation issues, so it's something to take advantage of where you can. The second one is abusing blind spots, where sometimes the sensor doesn't collect on or doesn't report on certain types of events. This could just be a configuration issue, or it could be a missing implementation in the software. Third is blending in, where the malicious activity we're performing fits in so well that it's hard for defenders to distinguish between what's benign and what's not. And lastly, we have sensor tampering, which I see as reducing the sensor's capabilities across any of these four processes. Decide is the next process, and this is where we deliberate on the options we've identified and then select a course of action. This is where we can consider what's important to us and then figure out what to do that best represents those values. So I usually look at this as a constraint satisfaction problem, and usually for red team ops, I try to pick the option that moves us closer to the operational goal, of course, is unlikely to be detected, and is a path of least resistance. But it's worth taking a step back and asking, well, why are those our constraints? Well, in my mind, one way we can decide on a course of action is to tie it to the engagement type. You might have internal penetration tests with the goal of achieving a certain scenario, but without needing to be covert, whereas something like that would matter for red team operations. And in some operations, there could be additional constraints that make it a top priority to reduce liabilities that lead to attribution and other consequences. But those constraints aren't likely to be the highest priority for most red team operations because if you get caught, the stakes aren't as high and you can eventually put your hands up and still say that it's the red team. I know there's definitely varying definitions when it comes to these engagement types, but in my mind, what matters most for this decision-making process is identifying the constraints that have been imposed and then evaluating our options against them. So at this point, we're going to take a small detour, and I'll show another way to look at constraints by using 6 principles from Matthew Monti's Computer Network Exploitation, or CNE framework. He wrote about these in his book called Network Attacks and Exploitation, which is definitely a gem as far as offensive security books go. Although I'll try to spend the next few minutes describing these principles, I just can't quite do it justice here, so I'd recommend getting his book instead. It's not too long of a read, and you can probably just spend a weekend ingesting the material there. So after I go through these principles, I'll then map it back to how we can use them to make decisions during ops. So the first one here is knowledge, which is the broad and deep understanding of technology, people, and organizations. If we can think of this principle as being variable, then we might want to consider what type of skill set do we want to emulate. Could it be a script kiddie that can get some IP addresses and run tools against them? Or perhaps a more advanced adversary that not only understands the technology, but also the psychological characteristics of the people they're targeting, and be able to find gaps to exploit in the target enterprise's policy, their norms, and their organizational structure. The next one here is innovation, which is creating or adapting technology and methodology to new circumstances. So an example could be getting stuck on something, like maybe having a script not work, and then making adjustments to adapt it to its environment, and then you're good to go and you're not blocked anymore. So when I look at this as a variable, I see it as the degree to which we intend to demonstrate novel capabilities. Awareness involves mapping out the operational domain and being able to detect and monitor relevant events. So you can think of using Bloodhound as a good example, where you're actually mapping out AD domains and then digging through the company's internal wiki to identify targets that can help build awareness. But mapping out the operational domain is half of it. The other half is being able to get a sense of what's relevant to you in near real time where possible. And what you get when you combine these two is something like a Marauder's map. So with this, you can orient yourself in the environment and get a sense of where you should be going, but also be able to understand the likelihood and consequences of getting caught. Precaution is the fourth one, and this is about minimizing the impact of unwitting actions that are outside of your control. Let's say if a code base is refactored, then you might lose the backdoor that you've implanted into it. Or when ACLs change, you might lose your access. But the fact of the matter is that these things just occasionally happen as part of the day-to-day efforts in the target environment, usually without them knowing that you're there. So this is where adding points of access that are redundant and diverse come into play. Operational security is probably one that almost all of us actively think about during red team ops, and it involves minimizing these three things: the exposure, detection, and reaction to an operation. Lastly, we have program security, which is containing the damage caused by the compromise of an operation. Like I mentioned earlier, when real attackers get caught, there's more at stake and they can have a lot more to lose. There are liabilities around attribution, attacker infrastructure, and the exposure of private capabilities. So I think in most red teams, this is something that can be emulated to a degree, but for many places, whether the service is provided in-house or externally, at least from my experience, I'm not sure how common or even how appropriate an economic model would be that justifies the cost or investment of emulating this properly at a very high degree. But anyway, Matthew's book goes into this and other topics in detail, so it's definitely worth a read if this is something that interests you. So yeah, these are the principles I try to keep in mind while doing ops. I'm definitely not perfect at it, but I can see how they fit in the context of this OODA loop model. So whenever I have some attack path options available to me, I can decide on which to choose by looking at these principles as variables in a data type we can call a tradecraft policy. Each variable maps back to the degree to how much or how little we intend to demonstrate the principle, perhaps represented as a Likert scale. And then these variables become a mix of hard and soft constraints when a policy is defined. What this means is that any engagement type can be represented with a tradecraft policy. So as we review the options available to us, we can then evaluate them against the constraints, and then more objectively get a sense of how each of the available options score against the policy. And then we can pick one that's optimal, if there is one. Otherwise, we just pick one within the feasible region of options. And I'll say that the substance of this shouldn't be new to most of us. This is just kind of part of our intuition. But that said, I find it useful to have some sort of mental framework to cross-check that intuition and then be able to defend decisions that way. Now, when you bring these variables back to labels like red team, adversary emulation, internal pen test, and so on, I'll say with what we're seeing here, this isn't a perfect depiction, and there's certainly room for disagreement. But the idea is to put the labels aside and to think about what these engagement types mean based on the constraints imposed on them. For example, an internal pen test might take OPSEC less seriously than a red team op, and a red team op might take program security less seriously than a real-world offensive ops, so it's somewhat relative. Moving on, in the ACT process, this is where you execute on the decision you deliberated on to use as a TTP. For those of you familiar with the MITRE ATT&CK framework, you can think of an action as the same as executing on any of the TTPs here. And all of the OODA loop processes that occur before this one can explain how and why you chose your TTPs. In my mind, and I'm not sure if this is a fair interpretation, but I would expand the ACT process to include the things you do both in the operational environment and the non-operational environment. So in the operational environment, there are also administrative tasks like seeking guidance on targeting and tradecraft and also producing daily status reports. And in the non-operational environment, there's continual development with capabilities and infrastructure, and there's also continual self-growth. At this point, I'll move away from the abstract concepts and try to put some grounding on them by way of a simplified operational example. This over here is a sanitized and modified version of a scenario that I had encountered in the past, where there was an assumed breach starting point, and the goal was to get access to a server with the crown jewels. So starting with observe, we gather a lot of information during operations, usually at a faster pace than we can articulate, so for the sake of this scenario, I'll just go over a few. First, we have the data from our Sharpound collection, which includes groups, group memberships, active sessions, computers, and so on from the domain that we're targeting. We also have credentials for a utility service account that were found in a file at some point during the op. And then as we're traversing through the environment, we can see that this fancy EDR 2000 product is installed on most endpoints we come across, and that LSAS is lacking protections like Credential Guard or having PPL enabled. And in addition to the observations we make from the operational environment, from a self-growth standpoint, we have this growing knowledge of various LSAS dumping techniques. On the right, you can see our situation model, which is the mental representation of the situation described in our problem. Based on our Bloodhound data, there is a path available to this crown jewel server, but we can't directly authenticate to the server using the credentials that we currently have. So instead, we can pivot to a jump box which has an active session for an account that can authenticate to the target server. Another path also involves this Bertha Scott user. Now it turns out that the service account that we have access to, we can use that to change the password for this user, and we can use that to directly log into the crown jewel server. We can also tell from some previous experience, cross-checked with online searches, that this fancy EDR 2000 product actually isn't that fancy, in that it's good at detecting malicious command lines, but not much more than that. So we might be good if we manage not to use lolbins that have easily signatured command lines. And lastly, if we go with the credential dumping route, we can try to map our understanding of LSAS dumping techniques, the ones that we know about, to the operational environment. So here you can see that they're divided into techniques that can be invoked by certain command lines or processes versus techniques where you invoke specific Windows API functions. So it looks like we have a couple options from the Orient Phase to process to get to the crown jewel server, but the decide process is where we can apply constraints to make an optimal choice. In this scenario, we're doing a so-called internal penetration test with the blue team looped in, so OPSEC isn't really a high priority. But in the sense that if we're caught, it's not the end of the op and we can still keep going, but at the same time, we want to avoid denial of service where possible. So practically speaking, I think that dampers our ability to change Bertha Scott password, so we won't be able to get access to the crown jewels a bit more directly. Program security is considered important in the sense that if we have secret sauce for dumping credentials, we'd want to use them only when it fits the situation and the timing is right. We're also given some guidance to try to achieve the path of least resistance, so we could put a cap on capabilities that require higher levels of knowledge and innovation unless they're required. So what that means is we can put API-based LSAS dumping techniques on hold unless we need to use them. And that we know that the EDR is great at blocking processes with suspicious command lines, so to work around that, we can use Task Manager to dump LSAS over RDP, which wouldn't create a suspicious command line. Now we've effectively filtered down our options to one that we can act on. We can use the utility service account to RDP into the Jumpbox server. Then we can launch Task Manager, right-click, dump LSAS, and that can get us credentials or hashes for that Crown Jewel service account. And with those, we can finally laterally move to the Crown Jewel server for collection. So hopefully I didn't bore you too much with this section. The point here really isn't to show how to dump LSAS or any new operational technique. It's really just to spell out how the decision-making process in our day-to-day operations work fits into this OODA loop model, so that when we go into this next section on EDR evasion and try to apply the same model, we can see the parallels more clearly. And that brings us to the main question: how do we win against Ddr sensors? So most of the historic research I've read around EDR bypasses, they kind of look at them as a black box, in the sense that you just try throwing a bunch of payloads at them and you see what sticks. And you can also look at what alerts show up in a customer dashboard. And that collective experience is kind of what shapes how we decide on how to bypass products the next time we're up against them. The downside, though, is that we usually don't really see the technical reasons why something worked or why something failed. It just kind of ends up being anecdotal. And that's been changing. There continues to be a growing amount of public research on understanding per product internals and taking advantage of them. So from what I'm seeing, a larger subset of them focus on the observe part, like using unhooking, disabling ANSI, using direct syscalls to deliberately limit the EDR's visibility. And I think it's reasonable to approach it from this angle first, because it focuses on the sensor's perimeter, and we can more easily leverage existing knowledge of OS internals to understand how sensors interface with the OS. So in some way, this kind of serves as a path of least resistance. But there's also a smaller subset of offensive research that focuses on how the sensor makes sense of the raw events that it receives and how it reacts to them. And I'll go into these in the next few slides. But what I'm trying to convey here in this slide is that when we look at EDR sensors in this cognitive model, we should recognize that EDR sensors also have OODA loops, and that to win against them, using John Boyd's terms, you have to operate inside their OODA loops. So what this means to me is understanding EDR sensors and the context of each process of the loop, and then figuring out how to circumvent each process where appropriate. And the way I've approached this is to kind of loosely look at each process in the context of the CIA triad. From there, you'll also want to operate your offensive loop at a faster pace than the defensive loop. Although defenders have been catching up quickly, which is great, attackers still fundamentally have more agility by operating in smaller and nimble groups. So essentially, what you do is improve each process in your operator loop in a way that allows you to make better and faster choices than defenders. And as a result, this can create some ambiguity, confusion, paralysis maybe to some degree, but according to this model, it'll slow down their ability to respond. So that's a very high-level overview of how to win according to the OODA model, but I'm now going to dive a little deeper and take you through how EDRs work in the context of each process of the loop, and I'll try to go over how to circumvent each process in the context of the CIA triad and try to provide some examples as well. So real quick, I mentioned earlier that I was loosely applying the CIA triad to this. I'm not really sure if I'm using the best terms here or if we even need to be this granular, but I added this slide just to provide some more context. Basically, with confidentiality, you're not really tampering the sensor. It's just kind of more about deep dive research and analysis. You're really just learning more about it and how it's configured so that you can use that knowledge to win. But with integrity and availability, that's where it can involve some level of tampering, where you're shaping or disabling specific behaviors that work toward your interests but against the defender's interests. Starting with the observe process, this involves the intake of information, which includes observing both OS-level events and also accepting communications directed towards its different components. When the sensor decides to perform an action on a system, then it's also in a position to observe the events that unfold from that interaction. A few examples are listed here that include OS interactions like being able to monitor process creations, file writes, API usage, and so on. But there's also updates to signatures and models, as well as updates to the sensor's configuration and policy, which, as we'll go into the next sections, help respectively with the orient and decide processes. If we go back to the Task Manager LSAS dumping example, we can ask ourselves what raw events are available for a sensor to observe. So we don't have to get into the details as much because that could be a talk on its own, but with what we have listed here, we have a couple kernel mode callbacks that can let the sensor know about the creation of the Task Manager process, in addition to whether it created a process handle on LSAS. We also have an inline user mode hook for when Task Manager attempts to read process memory for LSAS, and another filter driver callback, which lets it know about the dump file being created in the temp folder. Now, I imagine there could be more relevant and redundant forms of telemetry, but just for the sake of example, I'll limit it to these. When it comes to attacking the observe process of the sensors loop, we have a few options available to us. First, we can get visibility into exactly what kind of telemetry is being collected from the OS. And that's where the telemetry sorcerer tool on the top right does for enumerating kernel mode callbacks, inline user mode hooks, and ETW providers. And it's worth spending the time to understand what each of these can capture and the value they provide, so that if you're tampering with sensors, it's done in a more meaningful way. And on that topic, a popular option these days tends to be around the removal of inline user mode hooks. But perhaps what's less common is keeping the hooks and instead patching the injected sensor DLL to prevent it from reporting the telemetry to its service component. A lot of sensors rely on kernel mode callbacks for telemetry around processes, threads, objects, files, the registry, and so on. And although patching those out would require higher privileges since you need to usually load a driver for it, anecdotally speaking, it looks like several products just don't detect this right away. With ETW, you can patch user mode API functions to disable reporting, and also use the Windows API to remove providers from trace sessions associated with products. And the last one that comes to mind is just getting familiar with the product's inter-process communication, or IPC channels, and use that as a way to spoof or tamper communications from other sensor components. Now, most of this probably isn't new, but for me, when I fit it into this OODA loop, it forces me to think about what I haven't considered from these other subsequent processes. But continuing on the observe process, I wanted to briefly introduce a small project I've been working on with help from the Wover, and it's something we'd like to open source in the future. It's called Flashbang, and basically it's a declarative-based capability for evasion. It borrows the fishlets concept from Evil Jinx, in that you can have these YAML blindlet files at a per product or per environment level, and each blindlet contains a sequence of actions like suppressing telemetry, which can abstract away the need to write code for stuff like this. Once a blindlet is enabled, you can start doing suspicious stuff with the telemetry collection suppressed, and then you can disable it, which will roll back the changes. You can see a few of these actions here, like suppressing telemetry or doing memory patching, some utility functions as well. And this embraces that model that there isn't a universal or silver bullet solution, but instead that there's a toolbox and this idea of creating templates to adapt to different products or situations. A small example here where you can see a payload from a blindlet on the left, and then on the right you can see output from Cobalt Strike when it's enabled. It's edited a little bit just to make it more readable on the slide, but you might want to pause or put this on full screen, where on the left you can see a driver setting object that gives you some flexibility in loading it. And then on the bottom you can see the sequence of actions like suppressing kernel mode callbacks, user mode hooks, as well as providers from a ETW session. So here's another example using a test harness against OpenEDR with some more verbose output. On the top right, you can see the blindlet, and at the bottom right, you can see the kernel mode callbacks and telemetry sorcerer, showing that they haven't been suppressed yet. Once it's enabled, though, you can refresh telemetry sorcerer and then be able to see that they're now suppressed. And it's at this point that you can start doing some malicious stuff with reduced risk of getting caught. And then you can disable it, which will just put it back to normal. Moving on to the Orient phase of the sensor loop, this is where it processes its observations to internalize them and then determine what its options are. If you recall from the operator loop, this is somewhat similar at a high level, but from the sensor side, this involves a few things. There's the continual process of building an internal situation model to represent the system, which kind of at a high level is similar to the crown jewels exercise we did in the earlier example. Then there's normalizing the raw events we get from the observe process so that it can be reasoned by the sensor. The event data gets synthesized into the situation model, which allows it to look for malicious activity through the use of signatures or models. And in the next few slides, I'll continue that LSAS dumping example to provide a more concrete but simplified flow of what you're seeing on this slide. So here's a simplified example of what a situation model could look like. You can have a variety of objects of different types, like sessions, users, processes, and files. Here, when the task manager process is created, that emits an event from the PSSetCreateProcessNotifyRoutine callback, which then gets normalized as a process_create event. It gets synthesized into the model, represented as the Bertha Scott user creating that process. Next, when we right-click the LSAS process and dump it, that results in Task Manager creating a process handle on LSAS, which gets normalized as a process access event. I've seen a few examples online where folks use direct syscalls to evade this, but in my understanding, that's not as relevant because the EDR may well be receiving relevant telemetry from the kernel mode callback instead of a user mode hook. So direct syscalls might not be the most helpful here. Third, when the memory of that process is read using the handle, that can get normalized into a process read event. And lastly, when the LSAS dump file is created, that can be normalized as a file create event. So something like this can be detected with a variety of behavioral signatures, each with their own pros and cons. Just for the sake of example, if there was a signature for Task Manager accessing LSAS, then what if you could just dump it from another process? Or if there was a rule to catch processes that are not running a system but are accessing LSAS, then what if we just elevated our agent or run our dumping process as system instead? I think as operators, we're sometimes in the dark on exactly how an EDR is detecting a certain technique, and we're usually in this brainstorming process to get around that. But if we could know more about what specific malicious behaviors the product is looking for, then the less it feels like we're taking a shot at in the dark, and the faster we get at developing tailored bypasses that are specific to the product and the environment that we're up against. When it comes to attacks, the brainstorming we just did about bypasses is something that we can enhance. If we can manage to recover the behavioral signatures from the sensors, we can also try to recover any on-sensor ML models or static signatures to do the same type of exercise, but the caveat to keep in mind is that not all of this detection logic is stored on sensors. It depends on the product, but if a product supports prevention while the endpoint is offline, I think it's fair to assume that whatever detection logic relevant for that should be available on sensor. That said, the caveat again is that there could be additional logic on the server side that we won't necessarily have visibility of. The other thing we can glean from deeper sensor analysis are software bugs and design or architectural issues. There are certain types of attack indicators like novel suspicious command lines for which EDR products can model and develop detections really quickly. But then there are other attack indicators that can be harder to model because maybe the telemetry isn't there, or it's unaccounted for in the way that events are being internalized in the sensor. Other times it isn't a modeling issue, but perhaps a consequence of the natural frictions or constraints imposed on a product, like endpoint resource utilization or privacy compliance. This depends on the product, but some common examples include being unable to scan large binaries or not being able to auto-upload suspected maldocs, respectively. So these modeling issues and these frictions, they can take longer to remediate, assuming that they have high enough priority, and that the capabilities that generally take advantage of them could potentially have a longer shelf life. On the integrity and availability side, you can try to modify detection logic or somehow try to degrade the functioning of that component. But in most products, that might end up triggering anti-tampering mechanisms. From a path of least resistance standpoint, I think the confidentiality attacks are a bit more practical and less risky, especially if you can get that level of introspection from a lab environment. But if it makes sense to go down the avenue of tampering, then it's worth considering some of the lower cost efforts you can do, like limiting its visibility, so that way you don't have to dig as deep into individual products. I've got a couple case studies I can go over for this section, the first one being by Kamiel on Twitter. They looked into attack surface reduction or ASR signatures for Windows Defender, and what they were able to do was extract and decompile relevant Lua scripts from VDM files, which are the resource files for the engine. And within those, you can see generic ASR parameters for each rule, like path exclusions and monitored locations. This is really powerful stuff because from an operator standpoint, it shines some light on why a bypass attempt would have worked or not worked by being able to see details like this. For example, if this rule to prevent LSAS dumping is enabled, one way we can try to bypass it is by registering a service host DLL, which could potentially trigger that path exclusion. So by recovering behavioral signatures like this, it gives us something to work with, at least as a starting point, instead of completely shooting in the dark. The second case study is about Cylance's ML model for file classification. The authors at Skylight Cyber published it a couple years ago, and I thought it was really interesting because there wasn't much like it at the time. These models, they contain a treasure trove of intellectual property, usually with a lot of training going into them to get them into a more workable state. But the thing is that when they're deployed on endpoints, developers can lose control over how that model is being used. And there's a couple things that you can do with it that they did as well. The first is to decouple the model from the product and build a test harness to validate potentially malicious files against them, so that way you can scan files without having the telemetry go up to the cloud. And the second, perhaps more interestingly, was to find biases in the model to come up with universal strings that you can use to pad any malicious binary with, which ends up confusing the model into making false negatives. So just showing a couple slides from their presentation, this one shows how they extracted the model file. And this one shows the test harness that they wrote for the file, where you have a file as input and an output score indicating whether it thinks that it's malicious or not. This one over here shows the result of the universal bypass that they found, where by mutating a variety of samples, they were able to create these false negative scenarios, which I thought was pretty cool stuff. Moving to decide as the next process, the sensor has to make decisions based on how it's configured. And as operators, this at a high level isn't too different to how we select a course of action based on formal rules of engagement and tradecraft policy. But there is a difference in that we can also make decisions from our intuition. And I'm not sure if we're quite there yet with sensors, where some sensors today primarily make decisions based on explicit rules and configurations, although not exclusively. Some examples where a sensor could take different directions based on its configuration include the degree to how much data should be collected or phoned home. Clearly, it could be too noisy to receive the full fire hose of raw data that the sensor itself is observing, so that has to be filtered further, but also configurable so that the customer can decide on the trade-off involved. And there could be more constraints on reducing network bandwidth or endpoint utilization, and avoiding potential legal and privacy issues with what's sent. Some sensors can also take action on malicious behavior based on how confident its detection is, which can include notifying the customer, and also automated prevention if configured. As far as attacks go, the main ones I consider is just being able to recover sensor configurations to something that's humanly readable, and also doing the analysis to understand how that data is being used in conditional logic throughout the sensor, whether that's something that's hard-coded or soft-coded. With tampering, I've had some success with manipulating those values or altering the logic by patching conditional jumps, but most sensors have some anti-tampering mechanisms like detecting when a handle is open to its service process or monitoring changes to its settings in the registry. So you'd likely have to find some workaround to that first, and how easy or how difficult that is really depends on the product. I've got a couple examples here just to visually show how configuration values could be stored. On the left, this product has different flags for the collection types it supports, so if you can pull these values on a target system, you can get a better sense of what you're up against. Similarly, on the right is a screenshot of MacRaber's script for parsing out sysmon configurations, which I thought was really cool, especially because this configuration, it has that granular logic of what it does and doesn't report on. Moving to the act process, this is where the sensor executes on the decisions it selected, And in understanding this, I find it useful to look at the sensor not as a monolithic agent, but rather as a patchwork of different components, each with their own capabilities for action. For example, a communications module could be responsible for sending telemetry to the cloud. An IR module could be responsible for responding to any server-side taskings, and a prevention module could handle terminating and deleting malware if it's configured to do so. When it comes to attacks, I think what interests me the most, at least in being enlightened, is getting visibility into the events generated by the sensor. Because once you have that, it can unlock the opportunity to build some capabilities with program security in mind, like building more secure lab environments to observe how sensors react to different TTPs. You can also attempt to selectively filter events, where the idea is that you intercept sensor events before they're phoned home, and then you filter out the ones that you don't want the server to see. It's something I've successfully tried in the past, and while I think it's an interesting concept, I personally haven't found any need to actually use a capability like this. Also, this might be easier on some products than others, so this and other tampering techniques are things that you might want to look at opportunistically, especially if it's something you can avoid having to do in the first place. I'll briefly dig into this notion of having an offline telemetry backend. I wrote about it in depth last year, so feel free to check out the link if that interests you. Basically, the idea is to treat an EDR sensor almost as if it's like malware in a contained environment, where you try to dissect its C2 protocols and communications. And at a high level, there are 3 steps to it, 2 of them required, 1 of them optional. The first one is capturing the raw event buffers from the sensor in real time or near real time. And then the second is recovering any schemas so that the buffers can be parsed to be more human readable. And optionally, the third is pointing the sensor to a mock server that you develop, which can collect the events and then ship them off to your own SIM. In the example here, we're using Elastic Stack, and with that, we can also build dashboard views to make better sense of the data that we're getting. Alright, so that pretty much covers the EDR sensors loop. So now let's get into conclusions and recap. We'll start by trying to directly answer that question of how do we win against EDR sensors by getting inside their OODA loops? Well, when we look at the observe process, my first recommendation is to identify the telemetry sources used by the sensors you're up against, and you can use that information to guide tradecraft and develop capabilities to blind or filter sensor events when needed. I first approached this by building off the works of others and creating telemetry sourcer, which helped me understand this aspect of sensors better. But the problem with that was that it was meant for lab environments and it couldn't easily be used from an operational standpoint. So I started writing Flashbang after that to operationalize the blinding capability in a flexible way where you can write configuration files for different products, similar to how we have fishlets in Evasion for different websites. The next recommendation is to get familiar with how telemetry flows between different components of the sensor, and see where you can find opportunities to tamper or interrupt that flow. Most sensors have a user mode and a kernel mode component, so you can leverage existing OS internals knowledge to dig into how IPC functions between those components. And like I mentioned earlier, an alternative to removing inline user mode hooks is to keep them there, but patch out functionality to prevent the injected sensor DLL from passing the telemetry to its core component. This is kind of similar to how user mode ETW reporting can be patched out as well. With Orient, there's certainly an opportunity to understand more deeply how sensors are able to identify malicious behavior. And when you're able to see how things work at a more granular level, it naturally becomes easier to develop capabilities that retain some level of stealth. So with that, the third recommendation is to get familiar with any on-sensor signatures or models at an ongoing technical level. Because by doing this, it keeps you inside the sensor's loop by knowing how techniques get detected. And it also builds a pipeline for bypass generation ideas to come to you for triage. The fourth recommendation is to get familiar with any design or architecture limitations or bugs in the product itself, because although some bypasses can be rendered ineffective with a quick signature update, others might need a software update which can take longer because of complexity and limited resources, so the bypasses that take advantage of that are more likely to retain some longevity. And in general, if you're in a position where you're continuously building a library of new capabilities and program security is something that matters, You can take somewhat of a mechanical ratchet approach where the new capabilities slowly graduate out of lab environments only when it's appropriate to do so. Especially if things are still working with less sophisticated techniques, it could be risky, depending on your tradecraft policy, to unnecessarily introduce more sophisticated capabilities in a live environment, because any opportunity to use a capability is also an opportunity to potentially expose it. In the design process, we can abuse sensor configuration details to get a better idea of how it's tuned for detection and prevention. There are already several pretty useful tools and scripts available for detecting the presence of a sensor on an endpoint, but we can take that a step further to parse local configurations and use that to guide tradecraft. In this script, we can see configuration data that's locally stored on the endpoint, which can include information about settings that you can abuse or be cautious about, as well as information about path exclusions and blacklisted hashes. Of course, the degree to how much or how little you can get really depends on the product that you're writing this kind of script for. The sixth recommendation is this notion of formalizing some of our operator intuition into reasoning, where we can build toward tradecraft suggestion tools that internalize operational awareness against tradecraft policies. I think when we encapsulate this concept into Clippy, it shows both the promise and the potential for poor execution that can come with something like this. And lastly, with ACT, the most utility I got out of this was getting direct visibility into the telemetry that sensors phone home. So having that offline telemetry backend was game-changing for my workflow because on one screen you can have a VM with a sensor where you're interactively exposing it to malicious stimuli, and on another screen you can see the telemetry it would have sent to the cloud without the risk of actually exposing that information about the malware. And of course, you can build a detonation lab on top of this and validate payloads headlessly. So when you combine this with whatever payload generator you use for initial access, this effectively serves as that fitness function. As you're automatically generating payloads with various configurations, you can programmatically throw them against this validator and filter out the ones that generate on-sensor detections or other suspicious telemetry. Zooming out a bit, we can ask ourselves, well, what does this partially imply for the present or future direction in the space of operations R&D? The first that comes to mind is introducing more data-driven EDR bypasses in addition to anecdotal ones, because instead of solely relying on our intuition, we can now have technical reasons to justify a bypass. You can get a higher level of confidence when you have direct knowledge of the signatures that are being bypassed, or the telemetry that is or isn't being sent by the sensor when it's exposed to certain stimuli. The second is to enhance operations with optimization techniques, such as those from operations research, evolutionary computation, or automated planning. In my mind, the decision-making process in OODA loops naturally led to what are called combinatorial optimization problems, where you're trying to find the best solution to a problem out of a very large set of possible solutions. And as operators, we're constantly trying to find that best attack path out of many that's optimized to fit with the situation as well as the tradecraft policy that we use for an engagement. So as we put more effort into bridging that gap between the data we get and the decisions we can make our OODA loop go faster, which is how you win according to this model. And it's interesting to see how automation efforts in this space can further tighten that timeline between observations and decisions. I hesitate to call this stuff AI only because it's kind of a buzzword and it's definitely an area I'm not deeply familiar with, but I see the value proposition from approaching things this way. So an example to think about is to model initial access payload generation as an optimization problem. I don't think there's enough time to go into this in detail, but feel free to pause if you can and take a look. On the left, you can see that there are collections of nodes that are linked with edges representing legal transitions from one node to another. We start at the top with a delivery vector and end all the way down to an action like executing shellcode. When we think of how to build out initial access capabilities, with this model, it just kind of boils down to adding more nodes to each collection and then creatively thinking of ways to add new edges to connect them. When we think about how to generate the best solution out of the many combinations here, we can add weights to the edges by scoring the nodes against the tradecraft policy that's being used. And doing this can give you a ranked list of potential solutions to choose from. From there, you can further filter down solutions by running them against a fitness function, namely that detonation lab with the private telemetry backend. This is where you can get a better approximation of whether a sensor with a representative configuration would have detected the payload without the risk of sending all that telemetry to the cloud. So, putting this all together, it helps reduce uncertainty, and it serves as a way of tightening that gap between what you see, what you know, and what you choose. Anyway, that was a bit of a mouthful, but I wanted to highlight the potential of taking this cognitive model a step further. Zooming out further, I think the quote that kind of captures the moral of the story is that to cut down a tree in 5 minutes, spend 3 minutes sharpening your axe. It's nothing new to a lot of us, but it's worth reminding ourselves to slow down, think, and prepare before we act. And the second thing was that as I was looking into this, it reinforced that notion that when you compare two things against the same model, you can sometimes gain some additional insights about each. So the insight I got about EDR sensors was this deeper understanding of how they attempt to emulate a decision-making process that's somewhat similar to our own, even if it's somewhat at an early stage for now. And the second insight for operations was this quantification of tradecraft policy to give sanity checks on our intuition, as I've been alluding to in previous slides. My next thought is that if we can actually quantify our tradecraft policy to some degree, how does that translate into the code level for developed capabilities? And as is common in InfoSec, if this is something that we're thinking about, where has it already been done or attempted? All right, well, that's all I have. Thank you so much for taking the time to watch this and listen to me say a bunch of stuff. I know that most of the technical details probably weren't novel to many of you, and of course my perspective is limited, but I hope that this generated some ideas and I convinced some of you to look at things with this OODA loop model, and to also recognize that this model is something that's much broader than its applications just for operations and EDR sensors. I also have DMs open and can continue this conversation where I can. And lastly, I wanted to thank those that reviewed this talk and thank the organizers of ZeefCon for hosting this.